CR, can you unmute your mic and just let me know that
Yes, sir.
all the students were informed regarding time?
Yes, sir. मैंने कल इन्फॉर्म कर दिया।
Okay. So at the moment 24 are online.
Yes, sir. 1-2 मिनट में मोस्ट स्टूडेंट आ जाएंगे।
Okay. And may I ask how many have watched video which I uploaded on MS Team folder recorded with section B? आपने CR देखी है वीडियो?
सर वो मेरे माइंड से निकल गया था।
जी क्या किया था?
सर वो माइंड याद नहीं रहा मुझे देखने का।
ओके, मैंने आपके पूरे सेक्शन को ये मैसेज किया था और थ्रू व्हाट्सएप के आपने वो असाइनमेंट सॉल्व करनी है ताकि मैं आपसे उस क्वेश्चन के ऊपर डिस्कशन करूं। एनीवन एल्स? इस तरह तो फिर ये मामला नहीं चलेगा कि जो वीडियो अपलोडेड है आपके फोल्डर में वो आप लोगों ने देखी नहीं है। अपना लेक्चर देखा आपने? जी अब्दुल्ला जाहिद, प्लीज अनम्यूट योर माइक। जी अब्दुल्ला, आपने अब तक जितनी भी रिकॉर्डेड वीडियोस हैं ऑनलाइन लेक्चर्स की या लास्ट मैंने लेक्चर अपलोड किया है वीडियो रिकॉर्डिंग, let me open the folder. In this recordings folder there are videos present and I have advised on WhatsApp group with CRs that please watch videos recorded with section B, 2 hours lecture which I have highlighted here. आपने ये वीडियोस देखी?
सर अभी ये लास्ट वीक वाली तो नहीं देखी, शुरू की कुछ देखी थी सर।
Okay. Any student from section A? Hassan, Amir, Anis, Ahmed, Asad Rahman, anyone from section A who is following the recorded lectures regularly? Maqsood Bajwa, please unmute your mic.
Yes sir.
जी मकसूद, आपने लेक्चर फॉलो कर रहे हैं या जस्ट ऐसे ही बस?
सर कर रहा हूँ ये, लेकिन इस सेक्शन बी वाला 2 आवर्स का नहीं देखा।
अच्छा, ओके। ओके, Okay, let me then start from the slide where I stopped in my last 1 hour lecture. So let me start recording. Okay, this determination of neutral axis, in case we are discussing the fluxural design of beam analysis and design of beams, location of neutral axis at ultimate condition is important to be fixed where it lies, because without this we cannot solve the analysis or design problem. So location of neutral axis at ultimate condition. Ultimate condition means that concrete strain when concrete strain will approach ultimate strain in top fiber, and ultimate strain, we mentioned that as per ACI code this value is 0.003. So corresponding to this, what is the steel strain, and the steel location with reference to the from the top edge of the beam, which is the maximum strained or stressed compression fiber, its distance is marked as D, effective depth. And at this instant, when concrete approached its ultimate strain, where is the neutral axis and its depth C is important. And the distance from neutral axis to the steel will be then D minus C. So this is the ultimate strain diagram corresponding to failure of concrete, because we declare the crushing strain of concrete will be 0.003, and this is the limit, and further strain in concrete we can't afford, or this will be the last stage in terms of section ultimate strength. However, corresponding to that, what is the epsilon s strain in steel? We will be using Greek letter epsilon and subscript S to indicate that it is the steel strain. This is important. There are two questions. Question 1 is, where is neutral axis? It means C at ultimate stage. And second question is that at ultimate stage, what is the strain in steel? And we are using the strain diagram, linear strain diagram. So here two cases are mentioned, case 1 and case 2. Case 1 is named as tension steel yielding at ultimate condition. It means the clear message is that it means epsilon S in this case will be at least equal to the yield strain of steel, and hence if epsilon S is equal to the yield strain of steel, it means the maximum stress as per USD, what we can use in terms of steel stress will be Fy, because in case of steel, Hooke's law is applicable, and for all steel grades we know the modulus of elasticity is 200,000 megapascal, and the steel grades 300, 420, 550, all grades will have the modulus of elasticity 200,000. So we can divide the grade with the modulus of elasticity to get yield strain. So it means for grade 300, epsilon y will be 0.0015, and for grade 420 it will be 0.0021. So case 1 means that when concrete approached ultimate strain limit, steel at that stage is either at its yield limit or greater. So it is greater than or equal to epsilon y. So a good behavior is when we get excessive yielding in steel before approaching of limiting strain in concrete. So it means it is undesirable that tension steel, once concrete approach its limiting strain, ultimate strain, tension steel is below yield limit. So epsilon S is less than the steel strain. Very much undesirable. Case 1 is also named as tension controlled behavior, because tension steel is actually controlling the behavior. So a lot of warning will be given by this section, by this member, which is tension controlled under reinforced before failure, while a section which is over reinforced, and we are talking about the maximum stressed sections, and a member which has the maximum stress section with this limiting condition that when concrete approached crushing, steel was below yield strain. That is also named as over-reinforced cross-section, over-reinforced member. So over-reinforced means that there is little or no warning before failure because energy absorbed will be less, steel will be underutilized, less cracking and sag will be visible, and all of a sudden, due to crushing in concrete, failure will take place because keep in mind that equilibrium at a section means C equal to T. So once it will be violated, failure will take place. So either C will drop to 0 or T will drop to 0. In either case, failure will take place. C drop to 0 means concrete crushed, while T was below yield strain, was not even stressed to yield limit. That means over-reinforced behavior. While T maximum utilized, its steel approach yielding, it entered the yield plateau, and even beyond it entered the strain hardening. And then a stage comes that concrete finally crushed is desirable because this lot of strain in steel bars on the tension side will result into cracking and sag and warning before failure. So area under the load deflection curve will be large. So more energy will be absorbed. So final failure will always be when concrete will crush. But before crushing of the concrete, we want to maximum utilize the steel strength. And as well as we want warning before failure. It is very rare that steel fractures. So when steel bars are very less in area, there may be a possibility that the instant modes of rupture will come and concrete will crack and burden tension will be shifted to steel bars. At the same stage, all of a sudden, steel fractures. Very rare. It may happen when you provide threads of bars, wires rather than bars. You forgot to provide area, reasonable area of steel. We will discuss that how much minimum area we must provide to avoid this kind of brittle, undesirable failure, that steel fractures. The other possibility may be that, which is undesirable, that slip takes place between steel and concrete. It means there was a poor bond between steel and concrete. Like for example, you are putting the steel bar in conduits. So there is no contact of the bar with the concrete. Loosely placed bars. Or you grease the bars, oil them before casting the concrete. Again, that oiling or greasing on the surface will not let the chemical adhesion between steel and concrete to develop and bond will be compromised. So it means that is not a reinforced concrete, that is actually a concrete with steel bars present inside, but they are loosely placed, they are not developing the composite action. So that may happen in case when during steel placement, normally we grease or oil the formwork so that later on we can dismantle or remove the plates. So while oiling the formwork, the applicator also oiled the bars. In that case, it is quite dangerous that oiling the bars will result into weakening the bond between steel and concrete. However, otherwise in good design, we want tension steel to yield excessively. It must enter yield plateau, lot of strain and warning occur, and then eventually concrete approach its limiting strain and failure will be declared. While case 2 is undesirable, that concrete crushed while steel is not stressed to even its yield limit. Now we want to discuss case 1, its equilibrium equation, and how to get the neutral axis depth. Because as I said earlier, that in strain diagram, we know the strain diagram is linear and we know the limiting strain of concrete, that is 0.003. We have fixed this ultimate strain as ACI recommended to use the ultimate strain as 0.003, which is conservatively selected. But at this stage, what is the neutral axis depth? And corresponding to that, what is the steel strain? These are two important questions which are to be answered. So in order to derive equation of equilibrium for case 1, where we know that simple equilibrium equation for longitudinal equilibrium on a cross section, T must be equal to C. We want to substitute the value of T and C. And what is T? T is actually area of steel multiplied by the stress in the steel bars, and stress into area of the steel bars will give us tensile force. Because below neutral axis, concrete contribution will be neglected because it is very small in developing equilibrium, longitudinal equilibrium. However, concrete contribution in bond, in fire protection, in preventing the rusting of the steel bars is very much important, but in terms of section equilibrium, its role below the neutral axis is negligible. However, its role in compression is quite dominant because CC is actually developed by the concrete. And in this equation of T, we replaced a Fs with Fy, assuming that since we have said it is a case 1, tension steel is yielding, so we have replaced Fs with Fy, so it is our judgment that if it is a tension steel yielding case, definitely then the maximum stress at section which we will be using in our ultimate stand design for case 1 when tension steel is yielding will be Fy. We will not be using higher than this value. As per USD, the maximum stress in steel in our equilibrium equations will be Fy. And in terms of concrete, CC since last lecture we have discussed that Whitney's uniform stress block 0.85 C prime, if multiplied with the area on which these uniform stresses are present, will be giving us concrete force Cc, which is making equilibrium with the steel. And the force applied Cc will be at a depth a by 2 from top, and location of T is known to us because from top it will be at a distance d, effective depth. So it means the in between forces, the distance, we can, you can say, calculate very easily, and that will be actually d minus a by 2 internal lever arm. When I put for T A as Fy and for Cc the corresponding components, I can keep A on one side because in this equilibrium equation I know each and everything except uniform stress block depth. And in this way I can calculate A value for case 1 very easily, because if I know the area of steel in the cross section, I am provided with the information regarding the steel and concrete grades. I know the width of the cross section, and I can then calculate A value. And A divided by beta 1 will give me C value. And so in this case, I can put C over here in my linear strain diagram. If I got C from this equilibrium equation and putting C over here from the equation, I can get epsilon S, because from similar triangles I can write this equation that epsilon S divided by d C is equal to 0.003 over C. C I got from the, and effective depth and C in denominator will be brought on the right hand side, so I can get epsilon S. This epsilon S, if it is greater than or at least equal to epsilon Y, it will be a hint that we are rightly considering tension steel yield and we are on target, that it is case 1 beam. But if at this stage we get epsilon S from the calculated C and it comes out to be not equal to or greater than epsilon Y, then our selection of Fy over here is wrong, and we need to restart the review process by taking Fs over here. And it means we are actually looking at the case 2 beam, in which when concrete will approach its limit, steel is at Fs, yield stress. That will be case 2 beam. Case 1 beam is much easier to analyze, and behaviorally it is also. And case 2 beam, which is over reinforced, undesirable, is little tough to analyze. I will talk about that in detail. At the moment, in case 1, once our check is okay and we have S greater than or at least equal to Fy, it means all our calculations are valid, and I can then write the capacity equation, internal movement resistance equation, first nominal, and then I can multiply the nominal with the nominal with the phi to get the ultimate movement resistance. In case of flexure, this value will be 0.9 if and only if epsilon s is greater than or at least actually at this stage I may say that it is greater than point equal to 0.005. So we will discuss in detail this strain threshold, that you will be surprised to know that I'm not using strain equal to epsilon y over here. I'm giving a number, a higher magnitude of strain, in order to utilize phi equal to 0.9. So on the strain diagram of steel, it means if I'm having grade 300 steel and 0.005 is the yield strain of steel. So if my epsilon s is equal to epsilon y, I will not be allowed to use 5.9. I will be allowed to use 5.65. But if my strain is 0.005, I am on the yield plateau, or bigger, then I will be allowed to use 5.9 because the section is more ductile, it has more warning, it is not with less or little warning, so I can reduce the capacity by 10%. In contrast, if epsilon s is just at epsilon y, phi will be 0.65, very strict reduction. And if it is in between epsilon y and 0.005, I need to linearly interpolate phi between 0.65 and 0.9. So this will be our topic in next slides. At the moment, I can say that this capacity reduction also needs some assessment, that how much phi I will select, and epsilon s will tell me that how much phi you can use in your capacity equation. So once we have in hand T or C, because on the previous slide we got the left hand side and right hand side of equation, and now it is the time, and our checks are also okay. Now it is the time that I can use either T into CC, sorry, either T into lever arm internal capacity, or C into lever arm. Both will give me nominal moment resistance Mn, and multiplying them with phi will then give me Mu. So I can use either T into lever arm, as it is over here, T into lever arm d minus a by 2, or I can use Cc into lever arm, as it is d minus a by 2. So in this way I will get nominal, both answer will be same, and multiplying them with phi will give me finally the design moment capacity, ultimate moment resistance at that section. And in this way capacity analysis is complete. I can get the moment resistance, ultimate moment resistance. And there are two more slides, and I want to just discuss them briefly. So, and then I want to solve one design example, which is actually an analysis problem, capacity analysis of a beam. So in case of beam depth selection, it is important to understand that when you will do the design, as a designer, it will be your decision that how much will be the width of the beam and the depth of the beam. You need to decide the size of the beam, and we call it proportioning beam cross section selection. While selecting the beam cross section, it is important to note that depth of the beam is inversely proportional, and in deflection equation, depth of the beam is inversely proportional with the cube power cube to the deflection, because it is EI in the denominator, and in I, segment of inertia, I is 1/12 BH cube, and H means the depth. So more the depth, less will be the deflection along the span. Yes, load in this deflection equation is in numerator, span is also in numerator, and based on end conditions, equation for deflection will be selected. The deflection will depend upon span, end conditions, loads, and as well as in reinforced concrete cross sections, steel grade will also be important. FY. And for high strength steel, deflection is more because there will be more rotation capacity. Epsilon y will be more. So more depth will be required to control the deflections when you are using high strength steel in the cross sections. So I can refer to table 9.3.1.1 of ACI 2318-2019, where for different steel grades 300, 420, 520, and based on different end conditions, simply spotted, one end continuous, both end continuous, cantilever, H is proposed to control the deflections. So to fulfill the serviceability requirements, so the deflection within limits, less crack widths are the serviceability checks. So deflection within limits, then ACI will suggest you to select H for a simply supported beam based on L by 20, span by 20. But if one end is continuous, then this 20 can be increased to 23. If both end continuous, then the denominator will increase to 26. And in this way, for cantilevers, you will find that the demand is quite big because tip of the cantilever will sag and deflection will be more. So more H is required if you compare different end conditions. So in terms of end conditions and based on 300 steel grades, you will get different proposals. But while the steel grade is increasing, so is an increase in the H value to control the deflections. So if for simply spotted we look at the H, for 300 if we require L by 20, for 520 we require L by 14. And for all end conditions you can check the different H required to control the deflections. So all this information we are going to utilize when I will design the beam cross section. But at the moment, I am more interested in performing a capacity analysis because what we have talked about case 1 and case 2, I just want to apply it on a beam problem which I have assigned to section B, and I was expecting that your section will also work on the same problem, but sadly you are not interested in watching the video or doing the assigned work. Now let me first propose one statement that there is a beam with known cross section. I am proposing that B is 300 millimeter, a 1 foot wide beam, and its gross depth is 450 millimeter. So it means 18-inch deep beam, 1 foot by 18 inch. Beam has inside 3 bars, three steel bars are present as reinforcement, and these bars are number 25. So in US customary, there are different designations. In US customary bars, we will share with you some design aids and tables. In different textbooks, you can find these design aids at the end of books. In ACI code, you can get the different bars and their designations along with the nominal dia and areas and weight per unit length. Number 25 has the nominal dia 25 millimeter dia, and it is deformed bar, and nominal area 510 millimeter square. It will not be exactly pi by 4 dB square because this bar has some deformations, lugs on the surface, so this nominal area will be calculated, and it is 510 millimeter square, the nominal area of these deformed bars, cross-sectional area. Such three bars are present in the cross-section. And in this beam, these steel bars which are present at the bottom, these are present at a distance from bottom 75 millimeter, and 75 millimeter is the distance from center of the bar to the beam soffit. So this is I am giving you. We will discuss why this 75, why not 50 or anything, any other dimension. So this will be our topic in next lectures. Covers and recommended ACI covers for different structural elements. So at the moment I am proposing. Thanks. So at the moment I am proposing that from base bottom to the center of the layer, cover is 75 millimeter. Cover to the center from base. So it means effective depth of this beam will be the distance from top compression face to the center will then be 450 minus 75. It will come out to be 375 millimeters. Beam is simply supported, and it has a span 5 meter, almost 15 to 16 feet span. This beam has a concrete grade, 28 days slender strength, 20 megapascal. And the steel bars used are of great yield strength, 300 megapascal. And you are asked to determine the capacity of this beam. It means the question is how much this beam can provide us movement resistance. This is the question, and we call it capacity analysis because in this question cross-sectional details, material strengths, span, end conditions, dimensions are known to us except its capacity. This is called capacity analysis. You are given with the drawing. You know each and every detail regarding the reinforcements, spans. You are asked to give us how much ultimate movement this beam can resist. This is my question. And what I have discussed on the slide, case 1 and case 2 beam, that will be applied here. And we got capacity equations that mu will be equal to phi into T into lever arm, or we can say that C into lever arm can give us internal movement resistance. So whenever you are asked to perform capacity analysis, first thing will be you will assume that it is case 1 beam. It is tension controlled under reinforced beam. And case 1 beam means that you will simply write that T equal to C and AS into Fy will be equal to 0.85 Fc prime into A into B. This is the equation of equilibrium, and this equilibrium I am looking at a section which is the mid span of the beam, because in this simply supported beam I am calculating the maximum movement resistance against uniformly distributed load, and it means actually I am investigating a movement resistance and based on end conditions and single span, actually I am calculating that UDL. because once I will get the mu, I will equate it with the maximum moment ordinate, which for simply supported end conditions will be WUL square by 8. So L span is given to me 5 meter. MU I have calculated from my analysis. So multiplying MU with 8 and dividing with 5 square will give me that UDL, that ultimate load per unit length, which I can put on this beam. And that is actually the question, that how much ultimate loads, uniformly distributed load, I can apply on this beam, and against that what will be the ultimate movement resistance this beam will offer. And considering that it is a case 1 beam, so as I said, your first assumption will be it is a case 1 beam. So considering that this beam is simply supported and the mid-span section will be maximum stressed, and at mid-span section I write the longitudinal equilibrium equation T equal to C, and keeping in mind this case 1, I am putting Fs as Fy and B is given, Fc prime is known, area steel is known. All I want to know is uniform stress block depth. I will keep A on one side and I will arrange it like that as Fy divided by 0.85 Fc prime into B. Now since I have 3 bars, so 3 into 510, because 1 bar has the area 510, into the steel grade given was 300, divided by 0.85 Fc prime 20. I'm keeping megapascal in numerator and 20 megapascal in denominator, and B as 300. So can you give me answer how much uniform stress block depth will be? Three into 510 into 300.
Sir, it's 90.
It's 90. So 90 millimeter is the uniform stress block depth. Don't forget this picture. Actually, you got this A equal to 90. And now C you can get actual neutral axis depth, because this A is the uniform stress block. This simplified approach by Whitney. And C will be A over beta 1, because we proved that the relationship between the actual neutral axis and uniform stress block depth is A equal to beta 1 C. Since concrete grade is 20, beta 1 will be 0.85. So how much will be C? 90 divided by 0.85.
Sir, it's 105.9.
105.9 millimeter. Agreed? Now, if this C is 109.5 and this ultimate strain, as ACI has fixed this crushing strain as 0.003, what is epsilon s corresponding to this neutral axis depth C is an important check, because I have mentioned in my equilibrium equation T equal to C, and T I considered AS into Fy. So over there I assume that steel will be at yield, and based on this assumption I got A. From A I got C. And now drawing the strain diagram and confirming that on this neutral axis depth, whether the epsilon s as assumed is equal to or greater than epsilon y. If answer will be yes, I will be happy because my assumption is okay and it is case 1 beam. If not, then I have to handle it like case 2 beam. And my assumption that once steel will yield and corresponding to that I will get a neutral axis, and at that neutral axis when I check based on my strain diagram that whether my assumption that steel yield at this neutral axis is valid or invalid, if assumption is invalid, it means I was wrong in my expectation that at this neutral axis depth steel will get yield. So I need to go back and revise my equation with ASFS, and then I have to handle it like a case 2 beam. Let's see what we get. If epsilon s I want now, from this linear strain diagram I can write like this: epsilon from similar triangles, that epsilon s over d minus c.
Excuse me, sir.
G please.
Sir, it's 105.9 C.
Okay, let me change. You divided 90 with 0.85, right?
Yes, sir.
Okay, 105.9.
Yes,
Okay.
sir. 105.9.
Okay, let it be 106, almost 106, right? So now let's find out using similar triangles equation 0.003 over C. This leg of triangle divided by this base must be equal to epsilon s divided by its base, because triangles are similar. So now let us put 0.003 divided by C, you said 105.9, and let me bring D minus C on this side. So D, as I said, was 375, because H minus cover and C is 105.9. How much is epsilon S?
Sir, 0.0076.
Wonderful. Epsilon S comes out to be, ये काइंडली दूसरे लोग भी इसको चेक करें, बाकी लोग भी इसको चेक करें। ये आंसर आता है पहले एएस को भी जो हमने we started, let me take you to that end slide, sorry. We selected 3 bars 510 and grade was 300 divided by 0.85, 20 grade of concrete into B, and A was 90, and from A you got C, and C was 105.9. Agreed? And from this now you got the epsilon S, and from simple strain diagram you mentioned that 0.00, check कर लें, 0.003 divided by 5.9 into 375 minus 15.9, तो आपने भी 0.075 बताया, कितना दोबारा बताएं?
Sir, 0.0076.
76, good. So it is the epsilon S. So as assumed, epsilon S is well above epsilon Y. So in terms of steel stress strain relationship, definitely it is on the yield plateau, and even it is above 0.005, which is very desirable strain limit. We will discuss it in next half of the lecture at the moment, but I can confidently state that since my check is okay, my epsilon S is greater than epsilon Y. So all our assumption that steel will be at yield is okay. And now it is the time to determine the internal capacity either by using phi into T into lever arm or phi into C into lever arm. Since epsilon S is even greater than 0.005, I mentioned in my lecture that 0.005 and above means phi can be 0.9. So I can now write the equation of movement as mu is equal to 5.9 AS, which is 3 into 510 into Fy, because now I have no doubt because epsilon S is greater than epsilon Y. AS into Fs into lever arm, and lever arm is D minus A by 2, and D is 375 minus A you calculated 90 by 2, so 375 into 90 by 2 is the lever arm. So can you multiply this 0.9, 5.9, area steel 3 into 5, 10, Fy 300. So I'm using the equation which I mentioned, that I am using the equation, this one, phi As Fy into lever arm. Can you respond? What
Yes, sir.
is G? How much?
136,323,000.
Good. जरा इस पे मुझे आप बताएं, मैं यहाँ लिख देता हूँ. अब आप जो मुझे आंसर दे रहे हो ना, keep in mind that we are using megapascal and then dimensions in millimeter. So your answer actually is coming out to be in Newton millimeter. The movement
Yes.
which you are telling me is Newton millimeter. So it is suggested to convert this into kilonewton and meter. So it means what you are telling me, divide this with 10 raised to the power 6.
Sir, 136.323.
So 136.3 kilonewton meter
Yes, sir.
is the moment resistance this beam can offer at ultimate stage. So knowing this, now it is the time that, based on my end conditions simply spotted and knowing the span, I can calculate the load which I can apply on this beam, because you will agree that normally the user or the client will be more interested in knowing what load I can put. Rather, if you tell him movement, they might not be very much well knowing what movement. Inch deep beam reinforced with 3 number 25 bars of grade 300 and concrete strength 20 megapascal, having a span 5 meter, can be subjected to a ultimate load of on the beam. Your beam will approach its limit, limiting strain, that ultimate load. During service life, you might not put the ultimate on the beam, but if this ultimate will come, your beam will respond with excessive yielding of steel and warning, and then eventually crushing at top due to failure of concrete. But well before failure, there will be lot of distress, cracking, straining on the bottom. Offensive sag will be appearing, and then finally, once this 43.6 will approach, failure will take place. So service load means that dead plus life, and ultimate means that when you put 1.2 dead plus 1.6 life, so the exaggerated loads, once they will be present, and then against them what movement it can resist, that you have it. So this is just very जी please.
सर हमने मोमेंट डिजाइन का सर दूसरा फॉर्मूला क्यों नहीं यूज किया?
सीसी वाला?
यस सर, FC B times A वाला.
जी बिल्कुल, वो to apply, but it is normally you can say preferable, because in case you will use CC and into lever arm, but before check whether your steel is yielded or not yielded, because that epsilon S and the checking of assumption that you use ASFY is very important. So once you have that assumption in hand, then your answer will be other parts. Let me use that. What will be C 0.85 into FC into B 300 into A 90. So this will be your CC. Then into the same D minus A by 2, which you have calculated here, into 5.9, because we have checked this assumption that our steel is yielded and there is no ambiguity in selecting phi equal to 0.9, because our epsilon S is even bigger than 0.005. So you must get the same answer even from CC into lever arm.
Yes sir, getting the same.
Because don't forget that you selected T into CC. Your equilibrium equation is both are equal. So there is absolutely no doubt that either you use T or C, you will get same answer. But I repeat, normally you will prefer T part of the equation. The reason is simple, that your judgment of the steel status and finally checking whether it is case 1 or case 2 will be based on the status of steel. Once you have the idea about the steel, it is quite easy to select the T part of the equation. we are going to discuss on next slides that both very from one equation we get very useful information, other we get another help, but both are acceptable. You can use any one of them, your answer will be same. This is a brief, simple capacity review problem which I solved. Now, let me end the show. Once I will select discard, because if I will keep, then all these writings will remain on my PowerPoint. I'm going to discard them, but in the recorded video, you will get all these comments and text. Now, what I want to share with you is one. I have already uploaded this ACI 318 document. So I just want to share with you one information. As I selected number 25 bar, and I said it is US customary, in almost all reinforced concrete textbooks and even in ACI code, my screen is visible. So are you following my screen?
Yes, sir.
Okay, good. So on this code, you will find that there is appendix A and appendix B. In appendix B, it is mentioned steel reinforcement information. So when you select this, so you will get as an aid to users of the ACI building code information on sizes, areas, masses of various steel reinforcement. And you will find that what I selected number 25, here the nominal dia exactly they are reporting 25.4 and size 510 millimeter square and nominal mass in kg per meter. In case of weight estimation, this will become very important in design. When you want to review the capacity or you are doing a new design, you want to select out of these bar numbers different bars. Normally in Pakistan, bar number 10, and in FPS system we call it number 3 bar, and in local language we call teen sutar. It is very commonly used among laborers, such you can say typical our local language words, teen sutar. This number 13 in SI system, but in FPS we use number 4, and in our local we call it char sutar. Actually 1/8 inch they name it as 1 sutar, and then 2 sutar, 3, इस तरह के local word, local typical अपने bar designation इस तरह मजदूर यूज करते हैं. So this number 10, then number 13, then very commonly used is number 19, and in FPS system this will be number 6. 3, 4, 5, 6. This number 5 is very less common. Even rolling mills, when you want to get this dia, not very commonly used. Number 10, number 13, number 19, then number very commonly practiced, these 4 sides. 10, number 3 in FPS, number 4 in FPS, number 6 in FPS and number 8 in FPS. So please memorize बार ये 4 बार नंबर 10, नंबर 13, नंबर 19 और नंबर 25। ये तो कम से कम आप अपनी मेमोरी में रखें, अपनी ब्रेन के अंदर, रादर हर दफा आप टेबल खोलें और इसको देखने चल पड़े। आई recommend you at least keep these 4 bars in your memory. Now one more, you can say, information. In ACI code, chapter 9 describes beams, and when you search ACI code in provision 9.7.1.1, in chapter 9, in provision 9.7.1.1. By the way, I have uploaded this document on your MS Team. You can download, and it's very useful to read this document because in commentary will lot of useful information, background research and experiments and technical discussion. Cover arrangement shall be ordnance. Now click on this 20.5.1. It will take me to that chapter 20, and chapter 20 is 25 is reinforcement details. So I consulted chapter 9, and provision of concrete cover has taken me to chapter 25. Now in chapter 25, it was stated 20.5.1 specified concrete cover, provisions for durability of steel reinforcement, and chapter 20 describes in provision 20.5.1 specified concrete cover. So when I go through this chapter, I get a very useful table. There are different provisions, you can read them, but I want to take you to that table directly, which will be important for you as a designer. You need to know results. Specified concrete cover for cast in place non-pre-stressed concrete members. So this information will be applicable for all non-pre-stressed reinforced concrete members. Now look at the concrete exposure, member, reinforcement and specified cover. And it is actually concrete cover. It is clear cover. It is not the cover to the center of the bar. Let me just draw one picture to give you this understand. You can see such pictures in different textbooks. When I have a cross section, sorry, let me cut this. Bar, and this T bar will be enveloped by a ring, we call it shear stirrup or ring. And what we are talking about, that cover is actually the clear cover, even below the ring, clear concrete cover. This recommendation of ACI, what we are discussing, is actually the clear cover. Then in order to get to the center of the bar, I have to add the ties dia plus half of the center, half of the to get the cover from center. And in your problem, I proposed you, now you will get idea that why I selected 75. Again, take ACI code table. Let me read this. Not exposed to weather or in contact with ground. So very conducive environment. Not severe weathering action, indoor, and not even in contact with the ground. So sulfate attacks from soil are not possible. And remember, it is stated beams, columns, pedestals, and tension ties. So it means interior beams, interior columns, primary reinforcement, stirrups, ties, spirals, and hoops. So it means it is the clear cover to the primary reinforcement, clear concrete cover. And don't forget, ACI recommends in beams and columns which are not exposed to weather, severe weathering action, indoor conditions, and nor they are in contact with the ground, the cover requirement is 40 millimeter clear cover. And in FPS system, we use 1.5 inch against this 40 millimeter, 1.5 inch. And at this stage, just for your information, in slabs, which will be our next topic, it is in beams and columns for both. Don't forget, for both it is 1.5 inch or 40 millimeter. And in slabs, which are again not exposed to severe weathering action, the recommended clear cover is 20 millimeter, and in FPS system we use 3/4 inch, 3 by 4 inch, 0.75 inch, 20 mm. For rest of the conditions, in case of footings, don't forget, footing is also our topic in next semester PRC2. Cast against and permanently in contact with the ground. It means all footings. The clear requirement is 75 millimeter. So this is very important information which you must keep in mind while deciding the covers. Now I try to sketch a good picture, but I can show you some pictures directly from the code where they have placed ties, and from that picture I can easily show you the is one more. Yeah, it's a very good picture. Now look at the beam bottom. Up to the bottom of the tie, that will be the cover 40 millimeter recommended by the code. Then this tie, if I have selected a tie, a ring, which is shear tie, our next topic, shear design of beams. Over there we will discuss these ties design. If I selected a tie dia number 10 millimeter tie, it means 40 from soffit to the lower side of the tie plus 10. It will become 50. Then furthermore, if I move to the center of this bar, and if this bar is number 25, so half of this will be 12.5. So it means 40 plus 10 plus 12.5. So mechanically, the answer from soffit to the center will then be 62.5 millimeters. Strictly speaking, if I have a sketch with me, I know the ties. If tie is suppose number 13, dia. So it means 40 plus 13, 53. 53 plus half of number, if I am selecting the longitudinal bar number 25, so half of it will be 12.5. So 53 plus 12.5, it will be 63.5, 64.5, 65.5, and then 66. So in this way, I need to sum up all the dimensions to get to the center of the steel, to get the cover. When the word will be used clear cover, then it means we are talking about the clear concrete. When the word will be used cover, it means cover from the bottom to the center of the steel. So don't forget that here when I searched the cover and I got this provision concrete cover or reinforcement shall be in accordance with 20.5.1, and I got to this, it is specified concrete cover. This section addresses concrete cover over reinforcement and does not include requirements for concrete cover over embedments, pipes. This is only the concrete cover over reinforcement. As protection of reinforcement from weather and other effects is measured from the concrete surface to the outermost surface of the reinforcement to which the cover requirements applies. So it means it is mix this cover with the cover which is from the edge of the beam to the center of the steel. When the word is used concrete cover in code, they are using concrete cover. In some textbooks, they further put a word cover. So it means then it means it is as the clear cover. And here in the table, they are using the table title word specified concrete cover. So if original at clear cover, there will be more clear information that it means all concrete which is enveloping the reinforcements. So this is one point which is important. Let me take you back to the folder of PRC1. So we finished one very simple problem of capacity analysis, and just we discussed case 1 and case 2, and furthermore I mentioned that when I have a strain diagram, from strain diagram, linear strain diagram, I can select I can determine the status of the strain in the steel bars if I know the neutral axis depth. Now, in this presentation, I want to discuss very important ratio, unitless ratio, and it is named as balanced steel ratio, and Greek letter rho with subscript B is used to define this ratio. And this balanced ratio, its definition is also very important, and its determination will help us to decide that our section is case 1 or case 2, whether it is tension controlled or it is over reinforced. So it is a dividing line between desirable and undesirable behavior. So this balanced steel ratio, I can derive one very simple equation to determine the balanced steel ratio. But before talking about this ratio on this slide, I just want to draw your attention that just few minutes ago, we have solved one problem, capacity analysis. And if you recall, what we determined was the capacity of that cross section, and the cross section was having 3 bars, number 25. This steel ratio, we call it reinforcement ratio. It's very important unitless ratio because it will help us to visualize that how much steel area is present in a cross section without taking into account this balanced ratio or any other type of ratios. But just if I ask you that the reinforcement ratio rho, the Greek letter rho will be used, is the ratio between area of steel in the cross section divided by the effective area of the cross section. Effective area means in Flugger, the area which will be involved will be width of the cross section into the effective depth. So keep in mind that when you are talking about the reinforcement ratio, in flexural members, you will not use in the denominator gross depth, but effective depth, because the cover concrete is not utilized in movement resistance. So we call effective area is B into effective depth. And in numerator, we have how much area of steel is present in this effective area. The problem which we solved just a few minutes ago, if I ask you that can we calculate the reinforcement ratio of that cross section? Yes, we can. It's very easy. We had 3 bars, each of area 510. Number 25 divided by the cross section had width 300 by effective depth was 375. So can you give me reinforcement ratio in that cross section? Can you calculate, please?
Sir, 0.0136.
0.0136. Good. 0.0136. It will be normally reported like this. And in some situations, we may as percentage by my report that reinforcement ratio is actually 1.36%. Sorry. So when you will multiply it with 0.0136 multiply by 100, you will get 1.36%. Agreed? सही है?
Yes, sir.
Okay. So it means while the reinforcements in cross sections one you will be such ratios can give you a first hand information that what type of cross and you can measure that your action is whether case 1 or case 2. So row assessment also is inside. Not only this, that it is you will get perception that this cross section has 1.36% steel inside. So out of the effective area, you can comment that this cross section is concrete. So steel use is very small cross section. Fine, okay. This will also help you to classify your cross section. And for that purpose, we are actually discussing in next lecture also row max and then also row minimum. So all these rows are have classify the section. And code will to put rho in your cross section, which is 136 problem, always less than rho balanced. This is a mandatory clause that your rho should not be greater than and even equal to rho balanced. There will be another mandatory clause provision that should be greater than or minimum equal to rho minimum. So this is also one mandatory requirement. And furthermore, there is another very much important requirement as per under your ultimate stand design to design tension control cross that in design keep your rho or maximum equal to rho max. So if all these three conditions, that your rho is less than rho balanced, but it is greater than rho minimum, and ideally it is less than or at maximum equal to rho max, you are actually on target and your section is tension control, case 1, and not only it will give you warning before failure, but also it will not fracture all of a sudden because your rho is greater than rho minimum. If your rho will come out to be less than rho minimum, the chances of sudden failure after cracking of concrete in tension are there, or crack width will be very wide, and it is undesirable to keep the steel so less that it goes below rho minimum in the cross section. So just to give you the importance regarding rho, I spent this much time, but actually our target at the moment is to define the balance steel ratio rho B, and then to develop a small equation which we use to determine this rho balanced. In today's lecture, just final few minutes are left. Just I want to define this balance steel ratio with this strain diagram. Don't forget this diagram because this diagram will always help you to define the balance. This steel ratio or reinforcement cross section will result into crushing in the concrete and yielding in the steel at the state. The concrete will approach strain at the same instant approach its yield limit. That's why named as balance failure. So once concrete will approach this point, steel will approach this point. And script B used with the neutral axis depth to signify that it is not a ordinary neutral axis depth, it is the balanced corresponding is reinforcement show B. We will failure as balanced failure. And balanced failure means that concrete crushing
and steel yielding has taken place simultaneously. But what we actually require is steel should yield excessively, give us lot of eventually concrete should crush. This is what we desire. So this is the start of if concrete and approach of steel yield simultaneously is balanced, it means a little higher steel in the cross section will result into crushing in the concrete corresponding to non-yielding in the steel, which is highly undesirable, and we call it over-reinforced behavior. So balanced is the dividing line between under-reinforced and over-reinforced. So it means crushing and yielding is taking place simultaneously. And in all the equations of neutral axis depth, we will put a subscript B. Even in uniform stress block depth, we will put a subscript B, just to signify that it is actually the balanced, corresponding to balanced failure, the uniform stress block depth or the neutral depth. So in next lecture, I will complete the small derivation of row balanced, and in this way we can further continue the discussion on under reinforced tension controlled cross sections. So if you have time, we can continue for next few minutes, but your CR said that you have to offer prayer. So at the moment 31 students are online.
Excuse me, sir.
Yes, please.
Yes, you was a little late from the class, so I don't know. Did you take the attendance or not?
I just have downloaded your attendance, and the recording is also present in the files folder, so you can watch the video. And I recommend section A to please watch video seriously and follow the class material, class lectures. Otherwise, you will be left behind.
Inshallah, inshallah.
Already we are on online ODL or online come distance learning program. Already we have less, you can say, direct interaction, and I'm using PowerPoint to describe the problems. So if you will not watch videos seriously, then it will be very difficult to get the contents 100%. So if you have any question, most welcome. I am still online. Danish Aslam 313. Can you unmute your mic? Okay, fine. जी दानिश, आज का लेक्चर समझ आया है? You can type if your mic is not working.